My name is Austin Bingham, and today I'm going to be talking about, as you can see, open decisions in architectural evolution. This is a talk not about something that I or anybody invented. It's more of a, this material came from observations that I and colleagues have made about different processes, essentially, that have been used in different projects, open source, closed source, private, public, that are superficially different in many ways, but actually have some very powerful commonalities, and I wanted to try to find and understand those commonalities, to kind of like bottle the essence, the important things, and understand why these processes seem to work. I specifically am talking about architectural evolution here because this is the Software Architect Conference. I thought it would be a catchier title. But really, the things I'm talking about here can be used for designs of all scales. It doesn't have to be something architectural, some massive change. But that is kind of what we'll focus on most in this presentation. Does this work? Right, I'm supposed to remind you all, this is to remind me to remind you to download the app and fill in the survey. This is how the conference people get feedback, and it's actually very valuable feedback for me as well, so you can tell me if I did poorly or did well. So please do that. You should all have internet access at this point. So just a little bit about myself. I'm originally from Austin, Texas, this orange dot down here, so any other UT students, all right, hook 'em horns. That's where I kind of grew up. It's a great city. And why is this not, I'm just going to have to stand here, I think. I like this picture of Austin, Austin the city, not Austin me. This is a statue of a famous local musician, Stevie Ray Vaughan, and in the background is the skyline. It gives you a flavor for what the city of Austin is like. It's very proud of its music. It's very into it. They're the live capital music of the world. It's a very pretty place, very hot though. About 6 years ago, I moved to Stavanger, Norway. They're on the west coast of Norway, and this is what it looks like there. This is literally about 30 minutes from my house. This is Lysefjord. The best fjord in the country. Don't let anybody tell you otherwise. It's really, really, really beautiful when it's sunshiny, which is 10% of the time. The statues in Stavanger are slightly different, though. These are the three swords. These are 30-foot tall, massive stone swords rammed into the ground, not too far from my house. These commemorate the joining of the three ancient medieval kingdoms of Norway into what we sort of can call modern Norway now. So there's a big sea battle out in that fjord behind the swords, and that's no, things are a bit different. They're both wonderful places. If you've never been, you should visit. And of course, 60 North is a company I work for and own and founded up in Norway. So enough about me. First, we have to talk about, if we want to talk about using open design proposals, which we'll get to, for architectural evolution, we should have a common understanding of what we mean by architectural evolution. So, does anybody recognize this building? Maybe. So this is the City Court building in Manhattan. This is actually not the City Court building. This is a Lego rendition of the City Court building. It was the best picture I could find of it. It's certainly the prettiest. This was built back in 1977 by an architect named William Lemessurier. I think I'm pronouncing that correctly. An American with a French last name, so I have trouble saying it. So what is architectural evolution? Changes to architecturally relevant aspects of a system, and particularly to the form of that architecture. There's a distinction in some circles between form and structure in architecture, form being the abstract shape of the architecture and structure being technology applied onto that. People like Jim Copleen like this distinction, and I find it useful. So I am talking mostly about the form of the architecture, changing the shape of the architecture, not so much the choices you've made in implementing it. But I put this picture of this building up because it speaks to the difficulty of architectural evolution. If you've all been through large changes in large systems, you know what I'm talking about. But one thing that stands out with this building, one of the most important things, is if you look on the sides, it's standing on these strange stilts. And it's standing on these strange stilts because there's a church right here. Before this building was built, there was a church, the Lutheran church of some sort, I forget, I've got a note, but I can't see it, that said, fine, you can build a skyscraper here, but you can't move us. We're going to stay in the middle of Manhattan because, of course, that's a great place for a church. So the architect said, well, okay, I think we can work with this. And he designed a system where the load-bearing parts of the building were on the faces of the skyscraper. And this is different from, of course, how almost all other skyscrapers are built. They have load bearing on the corners. It's a very well understood architecture that all of the skyscraper builders in New York understood and had dealt with for a long, long time. So this guy, Le Mesurier, had to come up with a way to keep this corner clear and build the building up. So he came up with this chevron bracing structure. I should have a picture of that, but I don't. But that focuses the weight. I'm not a civil engineer, but he focused the weight onto the sides, the faces here, and built the building. And mathematically, it all worked out. They could do all the calculations they needed, and they said that, yes, this building is not going to fall over. The building was very light, however, because of this new structure, and it meant that the building was going to sway more than normal in the wind. So they put a really clever thing at the top of the building, this 400-ton concrete block, which was controlled by computers. And so if the building sways this way, the computers move the concrete over this way, and the center of mass of the building is compensated for, and it doesn't sway quite as much. So really kind of cool. So you've got one architectural driver down here that forces you to evolve your understanding of skyscrapers, which is this church that you can't move, so you have to build around it, chevron bracing structures, light building, sways in the wind, so you put a concrete block at the top. Everything's fine. They build the building, and it stands. And then Le Mesurier gets an email, and not an email, this is back in the 70s, so I guess a piece of paper, a phone call perhaps, from a grad student. And this grad student says, so I was given your building as a study project, something to do some calculations on so that I can become an engineer and architect as good as you, because he was very famous. And I did these calculations, and it looks like the building might fall over, actually, because when they do calculations for wind resistance on buildings, they do them on the main faces of the building. That, in a standard, normal skyscraper with support at the corners, is the dominant wind factor. And so they did all those calculations and said, yeah, this building is fine. But they didn't calculate enough what they call cornering winds, winds that hit on the corner. And this graduate student wrote to one of the most famous architects on the planet and said, cornering winds are going to knock your building over. It's very susceptible to getting blown over by high winds, which can occur because you're in Manhattan, which is right by the ocean, and there are hurricanes in the North Atlantic. So he, of course, was a bit shocked. He did some calculations, and he determined that, indeed, this building could get knocked over by winds. Now, there are people working in this building now. This is in the middle of Manhattan. There are people all around. If this building falls over, it's catastrophic. Obviously not a good thing. So they basically work really hard to, well, there's actually an interesting twist I should throw in. There was a hurricane out in the ocean at the time. Right, so he calculated initially that once every 55 years, based on meteorological records, winds strong enough to knock this building over would come in off the ocean. So he thought he had some breathing space. But then he did a little more thinking and said, well, wait a second, if there's high winds, even if they're not high enough to knock the building over, things that happen during those kinds of meteorological events are things like power outages. And when the power goes out, that concrete block stops moving around because it's controlled by computers. So now he realizes every 16 years, a wind strong enough to knock the building can come along. So he's really scared now. So they have people inside the building during working hours basically adding rivets to the building to make it more rigid. They don't tell the people in the building about this, which is a little bit weird, but they did tell the police and the fire department, so there was an evacuation plan, but the people working in and around the building had no idea this was going on. So ultimately, they get the building fixed up. It's still standing today, and there's a nice Lego replica, which I assume is in Denmark somewhere, that you can go see. But this, I think, is a really great story with regards to architectural evolution, because it shows that even the smartest people doing things that we've been doing for thousands and thousands of years can make these nearly catastrophic mistakes. And we're doing software, which we've been doing for, let's say, 50 or 60 years, and these are really complex systems, and we are bound to have mistakes and screw things up along the way as well. And so what I want to talk about with architectural evolution is a tool, these open design proposals that can help us to avoid these kinds of problems. It's a simple tool, and I think you'll all agree, hopefully, that it's something useful, perhaps, for your organization. So, okay, we talked about building, we talked about architectural changes in physical structures. But what are the analogs in software? So I'll just kind of go through a few small examples to set the flavor. This is very apropos for sort of modern design, going from monolithic single process applications over to microservices or concurrent serial processing kind of stuff. Breaking things apart and running web services and all that stuff is all the rage, and for good reason. But making these kinds of changes bring with them all sorts of issues you have to deal with, not just software issues, but your whole organization has to be aware and adjust to these kinds of changes. Now you have to worry about things like the CAP theorem. You have to worry about concurrency and failing nodes, and not just a single failing process. And you might have to go and talk to your deployment team and say, look, this was pretty simple and you're good at it, but this is how things are now. We have to change how we do that. You may have to talk to your salespeople and say, hey, we might be able to sell just the yellow circle and not the whole thing, or maybe we can sell just those two things as a component. So that's something you have to not worry about, but actually consider when you make an architectural change like this, because an architect's job, in my view, is largely acting as the bridge between the technical end of the company and the rest of the company, sales and marketing, stuff like that. So it is part of the architect's purview, part of his job, or her job, to keep track of these relationships. So you have to talk to the deployment people, testing, sales, on and on and on. So this is something that maybe some of you have faced. You've had to deal with a change of this nature. Another sort of popular thing going on is this notion of event sourcing, where you have an application that was originally saving its data in some persistent final state, the Han Solo mode over here, where you just go to the database or the file system and pull up the latest state of the thing. Event sourcing, for those who don't know, is essentially storing all the changes to your system. So instead of storing objects, so to speak, you're storing a bunch of events. And if you want to get to the final state, you simply replay all the events. And it's a very powerful system with lots of great benefits, auditability, replay, historical branching, all that kind of stuff. Git is essentially an event-sourced application, if that gives you some sense of how it works. And it's gaining popularity, so people are maybe making a change like this. But just like the move from monolithic single applications to multiple microservices and stuff, you have a lot of things you have to think about. If you have customers, maybe very big, important customers, and I've worked at companies that were in this situation, who are reading your file format and bypassing your application, they're going to be pretty pissed off if they have business-critical things going on that suddenly break because you changed how your data is stored on a disk. So you have to think about how you communicate these changes to your customers, and this has to go through the proper channels if you're in a big company, which is, as Alan says, not agile, but it's reality for a lot of people. So these are the flavor of the things that I would call architectural changes. You've probably all experienced something along these lines. Basically, big cross-cutting changes to your system that spread tendrils out to all branches of your organization and all parts of the application. Right, so what complicates the kinds of things that architects have to deal with during architectural evolution? You have to think about things like deployment. You have to think about things like licensing. Okay, the microservice system, you might have to license things separately. If you're using some technology to help you do licensing, you have to think about licenses for your licensing software, in fact. It gets very complicated. You have to worry about your UI, legacy data compatibility. All these things have to be considered when you make some big cross-cutting changes, not just a software change. And so getting all input from all of the stakeholders in your company and outside your company, clients, is really critical. And it's a massively complex thing. Asking two people, which typically happens, you're at a company and they say, okay, you guys, you're the architects, go in this room, come up with a change, come up with the big change that's going to switch our software from mode A to mode B and get that done. But that's basically impossible. That is cognitively a massive job. Asking two people to connect all these dots and cross all the T's and dot all the I's is basically asking for failure. And even if you do get two geniuses or two very lucky architects who come up with a great change that does address all the stakeholder needs, they still have the problem of communicating the change they've made to the rest of the organization. They have to explain, okay, this is how event sourcing works, and so your APIs have to behave this way, and you can't do X, Y, and Z. And they have to explain to the salespeople, this is how we're going to sell it now because it doesn't come in a single box, it comes in 6 boxes, or something along those lines. So the act of writing down and communicating in a useful way the change that you've decided to make is a really important thing to do, and it's something we fail to do quite a bit. And open design proposals are a really helpful way to get things written down, and we'll see how that works in just a bit. Right, so really, what's a poor architect to do? You've got people yelling at you about, what about existing customer data? Or we only know C#, so we can't do this thing you asked us to do. Or what about the GPL? You're asking us to use this library. Does that infect everything we do? On and on and on. We need tools, basically. And I mean tools in a very general sense. Processes, techniques, actual software tools, physical tools, maybe, I don't know. Some people can use a hammer somehow to do their architectural changes. But we need support. Our brains simply can't deal with all of the complexity of a large change in a large system, or even a large change in a medium-sized system. Only in trivial systems can we really get these things right, just using our brains. Apologize for that. Right. So that leads us to a tool I'm going to talk about, open design proposals. There are a few key qualities to open design proposals that are important. And like I said, these come not from going into a lab and deciding, okay, we're going to come up with the best system for doing architectural changes. These come from observing how these kinds of changes are developed and communicated in successful projects in the real world. So we've looked at a number of them, and we'll look at some in detail, but I'm going to go over the highlights of what we call ODPs. One is that it's light enough or heavy enough. It's a bit of a process, it's some documentation, and it needs to be tailored. You need to use method tailoring, which I think is a term of art from Agile or Lean. But you take this method, such as it is, and you make it work for your organization, right? If you're a small organization that's really self-organizing very fast, maybe you just kind of do whatever you want. But if you're a larger organization with lots of stakeholders and lots of threads heading out all over the world, maybe you have to have something a bit more heavyweight, and we'll see that play out in reality in a little bit. The documents that you're producing, as you're producing them, are open, or they're public and open for comment. That doesn't mean necessarily open to the entire world, but within whatever domain, your company and your clients, just your project, it doesn't really matter. But they're open for all people who might have a stake in the project to come and look at and comment on. You use a standardized format. This is something that we see over and over in successful projects, so I think it's important. But this allows things like indexing, machine processing, and searching and so forth of the documents. And it's really, it's an aid to reuse of the documents for future work. And that goes hand in hand with this notion of archiving. You want to keep them around for a long time so you can look back and say, why did we make a decision? What was the discussion around the decision? Why did we reject some decision? Because you want to keep archived also the things you didn't do, because there were probably really good reasons for not doing them. And maybe the rules have changed in the future and you can now make some change that you rejected in the past. And finally, non-trivial review. I'm really big on this, and this is something you see in successful ODP related projects. And there's really strong research behind the utility of reviews, and we'll look at some of that science. It's some of the best science we have as software engineers, and it really behooves us to understand it and to apply it. It's something we don't do as often as we should. I'm going to bang that gavel quite a bit. But what do open design proposals lead to? Well, we've talked about this a bit, but you get well-documented, well-thought-out, well-communicated, high-quality decision-making. And this is one way of putting it all into a nutshell. So you end up with actual documents that people have looked at and people agree on the content and form of. You get well-thought-out documents because you've had input from all your stakeholders, if you've done things right. Because they're open, everybody can look at it, and everybody should be commenting on it. They're well communicated, again, because it's well documented. You've made sure that everybody understands what's in these documents. It's not just something that makes sense to the people who wrote it. It makes sense to all the people who have to react to the change you're making. And finally, high quality. You get the change that you need. You get the change that actually makes sense. Instead of getting some person's conception of what the change needs to be, it actually addresses all the needs, hopefully, of all the people that are going to be affected by this. And decision making, of course, you're making some kind of decision. And maybe I should have bolded the decision-making, because this is not just, again, for architectural changes. This is going to be for much smaller things, much more localized things, generally related to software for this audience, however. ODPs are based on experience. As I've said, we simply have seen these used in the wild and seen that they were successful. So I like the analogy to map making. For centuries, of course, humans have made maps. And we found that we only needed 4 colors if we had, these are the counties in Texas, so we only needed 4 colors to make sure that adjacent counties didn't have the same color. We knew this from experience. We knew that it worked. We'd never run into a case where it didn't work, but we couldn't prove it. We know people kind of tried and failed. And it wasn't until 1976, well after this map was made, that we actually had a mathematical proof by some guys whose names are written down, but I still can't see. Who proved that, yes, you only need 4 colors for a map of this nature. So we were doing things, we were making maps that were really effective and useful maps that map the entire world without having proved that one of the basic things we were doing in the map was actually correct. And ODPs are a bit like that. Open design proposals aren't proven, okay, the review aspect has a lot of research behind it, but we know, we've seen it work. And you may or may not like that. You may not buy my arguments based purely on that, but this is something that has been used over and over again and produces tangible results. I think I'm blocking the camera when I step in there. I should stop. But the subtitle, practical and believable. We know that it works, and it's believable because it's simple enough that you can see that it works for your organization. And this self-evidence, this notion of ODPs being self-evidently useful or not useful for your organization is really key. And this is double-entry bookkeeping from way back in the day. And double-entry bookkeeping is something that's now, it's law, I think, for most accountants all over the world. But it was an invention that was created, by Medici bankers hundreds of years ago, something along those lines. And the reason I put it up here is that open design proposals, when your organization encounters them, you'll be able to immediately tell if it's something that might be useful for you. So as somebody doing just personal checking, double-entry bookkeeping is maybe a bit over the top. Some people do it, I do it, but not everybody does it. It's perfectly fine. But if you're a bank, you almost certainly do it because it makes a lot of sense, and you know that it makes a lot of sense. Even if you'd never seen it before, somebody explains it to you the first time, you go, oh yeah, that is genius, that's what we're going to do. So the subtitle here, easy to grasp. It's an easy thing to understand. It makes sense. It's easy to get started with. You can use very lightweight tools that you probably already have inside your organization. It's easy to modify, tailor it to your own needs, and it's easy to move on if you decide it actually doesn't work for you. Maybe you have something better that works for you, your culture doesn't accept it, something like that. It's easy to abandon. And so it's very lightweight. At the same time, though, I said that we kind of see these things in the wild, but and that's how we know that they kind of work. But there's a lot of research, especially things related to reviews, that tell us the activities going on in open design proposals make a lot of sense. We can sort of retrofit our knowledge about reviews, for instance, to say, okay, that's why there are reviews in ODPs, because that leads to high-quality software that leads to high-quality decision-making. And we'll look at, in some detail, at a fair amount of this research, hopefully to convince you, even if you don't do reviews, even if you don't do ODPs, you start to do more reviews, perhaps, in the rest of your organization, because it's the key, often, to making good software. And in the end, this is not rocket science. You're going to recognize elements of this. You may be doing something like this already in your company, in which case I would love to talk to you. In fact, I want to make that point that I'm going to show a few examples of ODPs being used, and if you're using similar processes or maybe modifications or slightly different processes, I would love to have a discussion about what works for you and what doesn't work for you, and maybe there's things that I'm missing from my bullet list of what exemplifies ODPs. But none of this is rocket science. It's all very common sense, and that's why it's easy for people to grasp. I love this picture because it's correct, but not really the answer they're looking for. So, public examples of open design proposals. We'll look at two of them. The first one is Python enhancement proposals. This was really my first exposure to what I am now calling open design proposals. Who here uses Python or has dealt with PEPs in any way, shape? One, okay. Two, three, a few. Okay, great. This is this is a PEP, a Python enhancement proposal. I'll just keep calling them PEPs. It's a simple text document with some structure at the top. This, the PEP number, the title, blah, blah, blah. This is the common format that makes the machine processable, parsable, and indexable. And the rest is pretty much just free-form text that the users can put whatever they want into. So PEP 1, we were just looking at PEP 0 there, so it's the meta PEP, and there's another meta PEP called PEP 0 that describes what a PEP is supposed to be. And so I added some bold into what I think are important things here. Collecting community input. The idea here is that you want to make sure that all the people who might be interested in the change you're making to Python, and that Python uses PEPs for changes to the language, changes to core libraries, changes to processes within the Python community itself. So they want to collect community input, documenting the design decisions, and this is key. That they want to make sure that they know the reasons they've decided to do what they did. They want to record the conversations that were had. They want to record the actual designs and how they're going to be implemented and so forth. So there's a lot of detail that goes into PEPs. The PEP author is responsible for building consensus, and we'll see the word consensus show up again in a somewhat different, more complex ODP environment. The idea here is that you may have a great idea, but if you haven't thought about the ramifications of everything that it touches, and Python is a pretty big thing, so there's lots of people who are going to recognize that if you make that change, that means this is going to stop working, or that we have to change this API or something along those lines. That's the kind of stuff that a single person will just never get right in a big enough ecosystem of software. But if you get all the people who care about Python communicating and building consensus, you'll come up with a design with an architectural change that actually touches all the key points, the important points. And finally, documenting dissenting opinions, keeping track of the people who don't like what's going on, they think it's a bad decision, or documenting the fact that you had a design, it was discussed, and it was abandoned, but it's kept around. So you want to keep a record of people who disagree with changes that are made and changes that were proposed but were never kept, because that's a great historical record for going back and deciding maybe we can make that change now. Maybe we can actually, because the change of environment, change of technology, so forth, do new things. So, but remember consensus. That shows up again in a little bit. PEPs are relatively simple things. They're simple text files. They use, as I said, a standard format. They're version controlled, so they're kept in the, I guess, mercurial repository with the rest of the Python universe. Before a PEP is written, a lot of work goes on in just in the mailing list. So somebody comes to the mailing list and says, hey, I've got this great idea, we should have this new keyword, something, 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 and they talk about it, and generally that's rejected before there's a PEP even written. So lots of work goes on in the open even before a physical document, I say physical, but an actual document is created. But after the discussion goes on, the powers that be in Python might say, okay, yeah, that's actually a good idea, write a PEP. Okay. So all rejected PEPs, though, are also retained. PEPs are publicly accessible and discussed. You can go look them up now on your phone if you want. It's at, I don't know, peps.python.org or something along those lines. Interestingly, a reference implementation is often required. If you're proposing a change to the language or a library, this is a Python-specific kind of thing. They say you need to prove that it's going to work. So this is something that Python wants. They've tailored the method, ODPs, to their own needs, but not all instances of ODPs require a reference implementation. So this should clue you in that if you decide to use something like this system, you may not need that little bit at the end. That's not a core part of what I think is the utility of an open design proposal. So it's a very straightforward thing. As I said, this isn't rocket science, just circle the X. That's how you solve this problem. But you can see there's a lot of utility. It does bring in all the interested parties. It gets a nice document that everybody understands and has agreed upon the form of, and everybody's they've built the consensus around the design that's being used. And that has worked really, really well for Python. It went through major language transition just recently, and it's going strong. So this is the kind of, put proof in quotes, but proof that this kind of approach works. I mean, Python is a huge distributed project all over the world, but they can make these big changes relatively painlessly. I say that knowing some of the internals that go on in the language, but relatively painlessly from the outside, at least. So let's say the other side of the software world, in a sense, is Java. But Java has a very similar kind of thing. Who here uses Java? I expect to see. No, not an overwhelming. What do the rest of you use? I kid. They have a thing called Java specification requests, which, if you kind of tilt your head and squint, it's just a Python enhancement proposal. It's just a document created by the community to communicate and document a change you want to make to the system. Now, if you go to the Java Community Process website, you'll see this picture here. You'll see the pipeline that everything has to go through. You can tell immediately this has numbers on it, and it has things like expert group formed, early draft review. This is much more structured, much more rigid in some sense than what's going on in Python land. Let's look at the description of what a JSR is supposed to be. And again, I've added some bolding for the important stuff. The JCP produces high-quality specifications. That's the goal, is produce a specification that is going to give you the right solution, not just a solution, but the right solution, a solution that addresses all the needs of the stakeholders. Inclusive, consensus-based approach. Again, consensus shows up, and this is a key. They know that there are stakeholders all over the place who may be interested in the ramifications of the design changes that they're proposing in a JSR. So they want to make sure that they get agreement from everybody. If not agreement from everybody, at least a majority of agreement and enough agreement that the dissenters accept the change. Lots of text, lots of text, lots of text, lots of text. Agreement on the form and content of the draft is then built using an iterative process that allows an ever-widening audience to review and comment on the document. So they're hugging more people into the group as they go, right? It's not quite as open as Python's approach. From Python's approach, everything is open from the very beginning and everybody can be involved. Java's a bit more closed, a bit more contained, and it only brings people in a sort of shell structure. The inner core gets it first, then some more people, and eventually the whole world gets to see what's going on in a JSR. So you can see this has a lot of the same features as Python enhancement proposals, and it's also very successful. Java's also gone through some pretty big changes recently. We're at Java 8 now. I'm not a Java guy, but I think that's the highest number I've heard after the word Java, So I assume that this works fairly well for making the language evolve properly. Some of the details of JSRs, though, are quite different. It's initiated by the community. But an initial draft is written by a committee. So somebody may go into a mailing list or the community discussion list and say, hey, I think this is a good idea. But the first thing that's going to happen is that the Java community is going to set up an expert group that takes that and they write the first draft of whatever the design document is going to be. This is different from PEPs. In a PEP, it's just written by whoever sort of decides they want to write it. JSRs are much heavier than PEPs. But this is maybe the most important part here. That's by necessity. You figure Java is owned by Oracle. And Oracle is a big company with lots of vested interests all over the world in lots of things. They're interested in making a lot of money. This is not something that Python is terribly concerned about. Oracle has a lot of customers who have a lot of vested interests around the world, and they're also interested in making a lot of money. And so Oracle is interested in making sure that all these customers, all these clients, these really important stakeholders that pay their bills are listened to. And so they've set up a heavier weight process. They've tailored the method to their needs so that they can get the kind of feedback they need in a way that keeps everybody happy and franchises all of the stakeholders. Membership is required if you want to take part in any JSR-related activities, but it's free for individuals and it's, I don't know, not terribly expensive for companies. So again, you can see how fundamentally they're doing the same things. They're working in the open, or as open as is appropriate for their organization. They're trying to gather all the stakeholder input, and they're keeping it around. This is all archived, I guess I should have mentioned that, but this is all kept around for posterity. So they know the decisions that they've made, they know why they made them, and they know why they've rejected such decisions. So those are some open examples. So let's look at a few private examples, closed source ones. I've had to anonymize these, of course, because people don't want me spilling all the corporate beans. But the first company I'm going to talk about, I'm going to call it Initech, and they make red staplers. Does that joke land with anybody? Okay, go see Office Space. It's a great movie. That's unfair. Initech is a bad company in the movie, but this company I'm talking about is a wonderful company in many, many ways. But at a high level, this is the first time that I saw an ODP kind of system working in a corporate environment. And I wasn't thinking in these terms back then, but it all kind of came back to me when I was starting to think about this talk. So proposals are developed by teams. They have development teams who are working on some specific feature. And there's a standard file format, Word. That's what they use in the company. That's what everybody used because that's what the salespeople and the marketing people and the testing people, they all just used Word. So it wasn't a simple text document, but it was a standard format. Everything was archived on a central file server. There were big mailing list discussions, and there were big discussion meetings. Interestingly, there was a slide that Alan had up about, I think what was called guilds inside Spotify, was it? Yeah. And they had a similar idea there. They had like they didn't call it guilds, but I'll use that word. They had the UI guild, and they had the high-performance math guild and all these kinds of things. And these different guilds would be sure to send a liaison to any discussion meeting that they thought was something they needed to keep their fingers on. So this is a way that they kind of manage cross-cutting concerns. You had specific features and projects, but you also had these sort of cross-cutting things that meant a lot to the company in a more lateral kind of way. But the discussion meetings weren't closed. Anybody could go. If somebody thought they had valuable input, they could go to the discussion meeting. So very open, archived, everything is hashed out in the open. All the same flavors of ODPs that we saw in JSRs and PEPs. So maybe this rings a little bit closer to home for some of you who work in largest companies. This was not a huge company, but definitely a medium to large size company. And it worked great. You ended up with a great big repository of design documents that you could then go back and interrogate, and we did this all the time. We wanted to know, why does this behave in this very specific weird way? Well, we go back and find out that the chief mucky muck said that it had to work this way because if you didn't, then things would segfault. So okay, you just follow the rules. I guess an interesting twist at this company is things were almost never rejected. You almost never created or in my experience, you never created a design proposal that wasn't going to be accepted. It was assumed that you had this requirement because customers needed something to be done, so you were going to get it done one way or the other. So in my experience, you never went through a big process of developing the ODP and then throwing it out. So that's a wrinkle for this specific company. So that's all I can really say about them. The next company I actually know quite a bit more about because I helped them sort of develop their ODP system. We'll call them Virtucon, and they make laser sharks. Does that land with anybody? Austin Powers, come on, I'm dying up here. Again, this is unfair. It's a really great company to work for. They're not an evil, world-dominating corporation. But the ODP system we developed at Virtucon was actually designed for managing a large architectural change. We saw that we were facing this big complex change that was going to touch all sorts of parts of the organization and all sorts of parts of the software specifically, and we had to put something in place that we could do quickly, that included all the people that we wanted to be in part of the discussion, that kept design decisions around, and that fit with the culture. And I think this is really important. We saw that between PEPs and JSRs, between Python and Java, there's very distinct cultures, corporate versus open source, et cetera, et cetera. And so they made the process work for them. And so we made a process that we knew, or at least believed, would land well with our teams, the people we'd be working with. It was designed to promote accessibility and adoption. That is, we wanted it to spread as much as possible in the company because we wanted everybody to be submitting design proposals into the same place so that we could have a master repository, so to speak. We use simple text files, just restructured text, which is a markup language similar to Markdown. And all the discussion took place on mailing lists, in meetings, and in review tools. We actually used some software to help us do actual reviews of the documents and get recorded feedback. Interestingly, all the discussion that takes place in meetings is essentially lost. We never recorded things that went on in meetings unless it got transferred from the meeting notes or something like that. If somebody took notes and then put it into the document or into the review tool, it was lost. And that's something that we didn't consciously recognize, but I think was very important in retrospect. We should have been a little bit more conscious of the fact that important things happened in meetings that we weren't later on recording, and so we lost some threads in some of our design decisions. Something to keep in mind. It may be something to indicate that meetings are actually not the best way to do these kinds of things. Maybe using tools and using mailing lists is a much more appropriate method. And we'll look at some of the research about reviews and inspections in general. And there's quite a bit of research that says that meetings actually are not that important for things like reviews, despite some of the early research into inspections. The technologies we used, again, restructured text, we used Sphinx. Mailman, just a simple GNU Mailman installation for discussions, and it was great. It was indexed, it was fast, it was simple. We all knew how it worked. Everybody has email. We used Garrett for reviews. The results, though, were really, really nice, and this is still going on today. I'm not with the company anymore, but there were over 100 detailed reviewed design documents, and they're not all of stellar quality, but they're all of a high enough quality that we agreed that they were acceptable, that they communicated the design to the level that we needed it to be communicated. We all had a common understanding of what the design decision was when the document was done, unless it was rejected early. Some of them were just rejected very early as bad ideas. But we archived everything. It's all in a Git repository somewhere. Both the documents themselves, but also all the mailman traffic, all the mailing list traffic is kept around. And that turned out to be very, very useful for getting into the very fine details of why some decisions were made and why some things were rejected. And really, it became a really important record of implementation details of existing legacy systems as well. Things that were only in one person's head, in a different city, we could say, well, that was discussed on the mailing list a while back, so let's go back and use that as our record of how things work. But this last bullet is the most important, I think, a broad understanding of why and how the system was being constructed. Everybody on the development teams that was involved with things designed using this ODP-style system had equal understanding, or at least equal access to the information about how something was working. It wasn't locked up in any particular person's head. It made our bus factor massive. And bus factor is, how many people have to be run over by a bus before you can't continue development. So often that's 1 or 2 people in companies. I mean, in my experience, it's generally a very low number. And it was more on the order, 10 or 15 in these groups, because we had all seen these documents, we all had access to them, and we all knew that we could go to them and they were authoritative in terms of the design. So we could all work from them. Really important stuff. So those are 4 examples of what I call ODPs, and I think you probably have a pretty good sense now, or at least I hope you have a good sense of kind of what I'm talking about and where the bullets we talked about earlier all came from. So all those processes have superficially different characteristics. They look different from the outside, but they all have the same internal structure for the most part and the same important internal qualities. And that's why they were all able to use a system like that, a process like that, to plan and execute really complex changes. So let's talk a bit about the power of review. I mentioned that this is, I think, one of the cornerstones of not just ODPs, but software development in general. It's something that I like to talk about. So I put in a couple of slides about review. Review is a key part of ODPs because it means that you get people looking at things early, you get feedback early about what's good and bad, and you make sure that the requirements are solid and the design is solid from all perspectives. Real research into reviews, what were called inspections, and still are called inspections, goes back to 1976, this guy Michael Fagan at IBM. IBM was really interested in improving quality because they were a massive, and still are a massive software organization, and they wanted to see what can inspections and reviews do for us to improve quality. So Fagan came up with this sort of pipeline of things that happen. There's planning, overviews, preparations, meeting, rework, and a cycle, and finally you have some follow-up. And they kind of polished and fixed this system over many hundreds of reviews and detailed tracking of data. But this involves lots of meetings, specific roles in the meetings, like there's the author, there's the note keeper, there's the person running the meeting, making sure they stay on time, et cetera. There's a definite process. There's lots of data collection. This is key to what Fagan's work was all about, and a lot of metrics based on this data collection. And this line of research it started at IBM and continued for a long time at IBM under people like Tom Gilb, and then there's like Carl Wiegers, I'm not sure if it's a strong W or not, continue this, and it's going on today. We're still learning more and more about what works with reviews. And I think that it's a key strength of ODPs. Now, the work that Fagan did was it was groundbreaking in many ways. It showed that this kind of stuff could be studied, even if it could only really be studied in the large at a company like IBM or Motorola or HP, where they had a large enough pool of resources to draw from. But nevertheless, it started happening. Well, people later on started asking questions about, well, do we really have to have meetings? Because meetings are, at least outwardly, very expensive. You're taking a lot of engineers typically, putting them in a room for an hour or two. They're not doing anything at that point except reviewing. So can we get the benefits of what Fagan identified coming out of reviews and get them without people having to go into meetings and sort of break their day up and get out of the flow potentially, so forth. And he found that actually meetings were not critical for getting most of the benefits of review. And the approach he took, at least in this paper, was that he looked at the top 5 reasons managers cited for using meetings, and he just mechanically shot them all down and said, okay, synergy, you get that without meetings. And education, actually, education by observation is terrible, so just taking a junior person and putting them in a meeting to learn is not a useful way for them to learn. And he continues to go down there. And you can find these papers if you want. They're very interesting reading once you get into them. They're a bit dull at first. But an interesting number out of this research was that only 4% of defects were found in meetings. The rest of the defects they found were all found by people reading whatever artifact was being reviewed ahead of time. So they had to do that. They had to do some preparation. Everybody coming to the meeting had to do preparation. So they found almost everything they were going to find ahead of time. And only 4% of defects were found in meetings. So this gives you a sense of the economic balance of meetings versus individual review. Reading, they call it, I think, is the term of art. Further research by, Kelly and Shepard at the Royal Military College of Canada, I think, wanted to look at groups versus individuals for code reviews, and their line of research basically found the same things as Vauda found, that 1.7 defects per hour reading versus 1.2 defects per hour in a meeting. So reading is, in some sense, mathematically 50% more efficient, which is similar to what Vauda had found. So again, you get the sense that you don't need heavyweight meetings for reviews to be really useful, and this is why you see the style of review going on in ODPs, because people found that it's just effective. They see intuitively that it works, even if they've never read this research. They just know, they can feel that it works, and it produces good results. Even more evidence. This is the reading versus meetings for UML design. So we're not just talking about code review, we're talking about actually design documents, UML if you're into that kind of thing, which I think you should be. More people ought to be. UML is really wonderful in many ways. But they spent 75% of their time in meetings and only 25% reading, but they found 80% of the defects in reading and only 20% in meetings. And so again, you see this big disparity between the effort and money that goes into a meeting versus the actual results of that meeting. And if you want to sum up, in some sense, what this research is telling us, is that meetings are good for finding false positives. Meetings are pretty good. If I come in and I think I found 6 defects in my reading, and now we get a group together and everybody's talking about the defects they found, people will tell me, actually, that's not a defect. What you found, that's the way it's supposed to work, and it has to work that way because of this complex interaction with subsystem X or something like that. So keep them short and small. Find the false positives. Spend a little bit of time reviewing as a group, but don't let this be the primary way you do reviews. Now, I'm not telling you that that's how you have to operate. There's lots of research that says that meetings are actually really, really powerful, and it depends a lot on the kind of software you're making, the organization, the size, and so forth. But we know a lot about how this stuff works, and it behooves us as software developers, architects, engineers, if we want to become engineers, to know this stuff and try to apply it realistically in the work we do. Different ways of looking at reviews. This guy, Frank Blakely at HP, was comparing the effectiveness of inspections versus testing. This isn't entirely apropos to ODPs, but it's an interesting set of numbers. So what they did is they did a bunch of inspection, and they wrote down all of the defects that were found. And then they compared those defects with the testing procedures that were in place to test the system being built. And what they found was 21 defects in the inspection process, only 4 of which would have been found in testing. So those of you who are using testing in place of inspection, take this to heart, meditate on it a little bit. This is a bit eye-opening. And there's lots of reasons for this, and you can read about this in literature as well. A lot of this, though, is just driven by economics. A lot of the people who want to know why should we do inspections are asking, do inspections save us money? Can we make more money with inspections? And the answer is yes, effectively. I'm not going to read all these out, but you see things like, Hewlett-Packard, 10-to-1 ROI, saving $21 million per year. That's a lot of money. Maybe not so much for Hewlett-Packard, but for me, that would be a lot. All of these guys show similar things, that inspections pay for themselves, and more than pay for themselves. They earn you money. And I don't know exactly how this translates to open source projects like Python, except that we know that inspections basically improve ROI. They improve your income by improving your quality, and that's well understood. So that really is the key. Inspections are part of the ODP system, the ODP framework. I don't want to use that word, but I just did, because they improve quality. 2 final slides on inspections. One is that upstream inspection is very, very powerful. A lot of us, when we think about code reviews and reviews and inspections, we think of code reviews. We think of a bit of code has been written, look over it, look for bugs. And that's the mindset that a lot of us come out of college with, come out of different jobs with. But the fact is that you get more bang for your buck. All the indicators at this point are that you get much more return by doing inspection on things like contracts, requirements, design documents, and so forth. All the stuff upstream from code. And that's why ODPs want to build, that's why I think we should have inspection and review built into this notion of ODP. If you make some lightweight framework for your organization to do design document development, don't throw out the reviews. They're really, really important. So this is a great quote from Tom Gilbs, Optimizing Software Inspections. He's a big name in review, so I trust him. Belcore found 44% of all bugs were due to defects in requirements and design reaching the programmers, 44%. So if they had just done a better job of reviewing the requirements, which is not that hard, they would never have had what I call miswork, programmers doing work that they shouldn't have been doing in the first place. Now, there's a quote, and I can't find the source of the quote, but I know I read it somewhere. Basically, the gist of the quote is that programmers can do whatever you ask them to do, and they will do whatever you ask them to do. If you give them a requirement to do X, they'll do X, even if X is not the right thing to do based on what the customers actually need. I swear, this quote came from Peopleware or from Gerald Weinberg, something like that. If somebody knows where this is from, let me know. I would love to have actually the source of that, but I believe it's true. I mean, if you're a programmer, you kind of know this. They tell you what to do, and you can do it. It's not a big deal. You're proud of your ability to do this. So asking programmers to do the wrong thing is a massive, complete waste of time. And so review your requirements, review your contracts, review all your designs before you pass them on to your developers, if you work in that style, waterfall-ish. And reviews complete a loop. Putting reviews into ODPs have all sorts of ramifications beyond just improving the quality of the artifact you're creating now. Somebody generates an artifact, it goes through review. The output of that review is, A, to fix up that artifact, but also to give feedback to the person who made that artifact about what they did wrong. A requirement may be incomplete or maybe unclear. And if you tell people that, hey, this was unclear, this is unclear, this is unclear, the next time they make a requirements document, they'll be more clear about it. They don't want to be going through this feedback loop. You'll be educating them. And this is typically called defect prevention. So you're not just removing defects from artifacts, you're actually preventing the insertion of new defects in the future by educating the people who are involved in the artifact generation, be that open design proposals or source code or contracts or whatever. This is perhaps the most important outcome of reviews, because if you educate your workforce, if you educate the people on your project, they stop making mistakes and your quality goes up all the time. You don't spend any time removing defects anymore. You just don't get defects anymore. Wonderful, that's what we want. So I'll close out the review section with a kind of a big quote from Robert Glass. Research study after research study has shown that inspections can detect up to 90% of the errors in a software product before any test cases have been run. This signifies an extremely effective process. Yeah, 90% is a huge number. He goes on. The same studies show the cost of inspections is less than the cost of the testing that would be necessary to find the errors. What we have here is an effective process that's also cost-effective, and that's a pretty nice combination. So I think that nicely sums up the lesson about reviews and why reviews are such an important part of open design proposals, because they are the key to improving quality well beyond what we get out of testing, well beyond what we get out of, I'm going to say things like refactoring and writing clean code and so forth. This is the source. This is the wellspring from which quality really comes. If you want to know more, like I said, there's lots and lots of research into this, and you can read all about it. There's a few books here that I think are really good. Ask me for the slides later if you don't get them. But specifically, this one by Carl Riegers is really good, and Robert Glass's book is just fun. It's about all sorts of stuff, and it's a fun read. I want to throw another one in here, though, as a bit of a warning. And this was recommended to me by Seb Ross, who I think is in the room. He called me out on some graphs in another talk of mine, and so I read this book, and I was educated. It's a wonderful book that shoots down a lot of the assumptions that we make about software development, the cost curve, given over time and things like that, or the cone of uncertainty. And he really looks at the research behind those and often tells you that really the research doesn't support some of the things we believe. And this will make you skeptical. As you read the review literature, this will give you a skeptical mindset, which is what you need. Don't trust everything that you read, but academic papers come across as very authoritative looking, and so you need to educate yourself. You need to put yourself in a mindset where you don't just blindly accept all this information. And it's a fun read, short read. You can get it at EPUB. You could have it now. You have it in 5 seconds. Go to the website and download it. I don't have the link, though. So I'm getting close to the end here, and so we're going to end a bit early, I think, but I've got a few more sections. I want to look at the benefits of open design proposals as I've described them here. There are a number of things that are pretty obvious. I think you get high-quality designs and so forth out of it, but let's try to wrap this up in a little gift. So in a nutshell, ODPs give you improved quality through communication. That's really the key to what's going on. That's the similarity between all of the different ODP implementations we've talked about. So quality meaning you get a solution out that actually addresses all of the critical needs. So you're making this massive change that's going to touch all parts of your organization. The quality is that you actually do address all of their needs. You don't just ignore some big tranche of your team or your company or your customers, which would probably be the worst. Through communication, right? Through reviews, through talking to one another, through having mailing lists, through keeping things open and allowing everybody to have input. So I could have just started with this slide and said that we're done, have fun, go home. But this sort of sums up what I think is the real key, the gist of why open design proposals are useful and why we see them happening over and over again in different guises and why you might want to implement one of your own. They allow you to harness the power of peer review. Okay, we really went over a lot of the why this is important. So this is something you should be doing whether or not you ever make an ODP or not. Do a lot of review. Consider using it more in your organization. It pays for itself. And you get the feedback early, too. It's hard to read, I guess, but do the review. As soon as you generate some change, have it reviewed immediately, because then you get the feedback very quickly, and you don't let bad changes propagate through your system. So do reviews in a very timely manner, and tools help you to do this. This is something that maybe is personal to my psychology, but I think it's really powerful. What I call the straw man effect. If I come up to you and say, well, I've got this idea for change, and it's going to be kind of like this, and we're going to modify this subsystem, and it's going to send this message, blah, blah. We can kind of chat about it, and maybe we'll come to a good design. But I find that if I write down very concretely a full design, or at least close to full design, and I give it to somebody, I get much better feedback. And I know I give much better feedback to a complete document. So I call it the straw man effect because you want to put something concrete in front of people for review, for discussion, and then that becomes the nexus through which the entire discussion can flow. It becomes much more focused, much more concrete, and you get much better feedback and much better designs in the end. You may have to iterate several times with a couple of straw men, but if you want to talk about the benefits of llamas, some of these are true, but they're not great for jousting. They probably don't speak 7 languages. So by putting this in front of you, we can really narrow down what's good about llamas. There's A guy I've seen give a couple presentations, Damian Conway, you may have seen him at some other conferences. I think that's his job, is he speaks at conferences. And he has a talk he gives on how to write talks. And one thing he says to do, which I think is really true, is you want to give a talk, so you try to come up with like the 5 things you're going to talk about. He says don't go more than 5 because that's too many. So one way to try to do that is you sit down with a blank piece of paper and you try to think of the 5 top things you should talk about, the 5 most important elements of, I don't know, mock test systems or whatever it is you want to talk about. And that's really, really hard because your brain is constantly kind of scanning and having trouble ordering things in your brain. You're trying to get the top 5, not just any 5. What he says to do instead is write down all the things you know about this topic. Once you're done with that, you circle the top 5. And those are your top 5 topics to talk about. It's a much easier system, and I know from experience that works. And I think it's very similar to this. By having something concrete in front of you, you spend a lot less time having these sort of nebulous brain paths that you follow and thought patterns. You can focus on exactly what might be wrong, and you can very easily see how the proposed design is going to affect all the things you're really concerned about, your stake in the enterprise, so to speak. Also, writing aids thinking. The ODP's part of why I include a physical, actual document as a necessity is that it forces us to write things down, right? And this, something about writing things down, it's the same as speaking about something. It forces us to verbalize an idea, and that helps us see an idea from a whole new perspective somehow. There is research behind this, but I'm not enough of a psychologist to really present it. But this manifests itself as this notion of rubber ducking, which I'm sure some of you have heard about, but you've probably experienced this. You're sitting down and you're trying to debug something, and it's just driving you nuts. You can't figure out why this is not working, and you spend all day on it, and finally you kind of give up, and you decide to walk over to your neighbor and say, hey, Jane, why I'm having trouble debugging this, and this is what's going on. And about 15 seconds into that discussion, your brain tells you what's going on. It's figured it out because you started talking about it. Right? So you don't need a neighbor. You don't need to go talk to Jane. You can just have a rubber duck on your desk. So if you ever get stuck, pick up the rubber duck, explain your problem to the rubber duck, and you'll have a solution. And that's very similar, I feel, to forcing yourself to write out a design rather than just talk about it in the abstract and then hope that you get the right design. Hope you get a good implementation or a good complete solution in the end. So, A, go get a rubber duck. They really work. But write things down. Even if you don't do ODPs per se, write things down. I think you'll find that it's a little bit onerous at first, but it actually frees your mind up and you get really great results from it. A huge benefit is that you enfranchise and inform all the developers on your team. If you think about what the developers are going to have to do once you've come up with a design, they're going to have to implement it. They're going to have to make sure that they know what you're talking about, that the coding they do actually follows the spirit of what you're trying to accomplish, and that they can tell when they're starting to deviate from that, or they can see when somebody else is starting to deviate from that. So having the design written down in a concrete form that everybody agrees they understand is a real key to making sure that the implementation work, the building of the Tower of Babel, so to speak, which this is MC Escher woodcut here, takes place as planned, right? Is that coming through? Yeah, I love that picture. I mean, you guys got guys up here who are just kind of yakking. Some are laying down. I think there's some guy drinking somewhere. But if this is your organization, then all right, it's a fun place to work. Finally, by keeping things around, by keeping all your decisions and your discussions around, you have an archive of your designs. You have an archive of all the wisdom that's gone in to what you have spent a lot of time trying to put together. And this pays for itself in the future, because when you come back to try to understand how the system works, you have a written down record. And this is massively useful. A lot of organizations have no history like this. They've got a product, they have people who kind of know how parts of it work, and that's it. By forcing yourself, that sounds a bit brutal, but by having the discipline to write things down and put it through review and have everybody see how things work, you have this wonderful record of what you've done and what you've rejected and the reasons why. This picture I actually decided is actually not a very good picture because it's from Indiana Jones, the Raiders of the Lost Ark. And they took the Ark, put it in a box, and hid it away somewhere, never to be seen again, which is actually not what I'm asking you to do. I'm asking you to index it somewhere and have it be searchable. So don't take this too literally. But yeah, it's a good picture. So how do you get started? We got plenty of time. I'm just going to spend a little bit of time, just 2 slides really, talking about what are the basics, what is the bare minimum you can do to get started. And chances are you've got this infrastructure already in your organization, because all you really need are mailing lists and a web server. If you can have open discussions via email, which pretty much everybody uses in companies these days. With the exception of Facebook, I found out that they actually use Facebook groups to do development at Facebook the other day. We were talking with Kent Beck at JavaZone, and he said, yeah, they don't use email, they use Facebook. And duh, it makes sense once you hear it, but it hadn't occurred to me that that was the case. So if you have a mailing list, you can have your discussions about the documents, and you have a web server that's serving up the documents that you're designing, you have fundamentally what you need to try this out. And so you can bootstrap a process like this very easily and try it on a small project or maybe a larger design and see if it works for you. And grow it organically as you need. This is the method tailoring end of things. But you can start to add in things like review tools like Garrett or Code Collaborator or all these other tools that exist. Toss in revision control, which you probably already have, of course, already. You can throw in meetings. If you decide the organization actually is sort of complex enough or needs that kind of structure because of your culture, have meetings. Or if the code you're writing is, it's going to drive a pacemaker or something, you should probably have some meetings to do some more formal reviews than just Garrett. You can pick different document formats. You can have all sorts of processes built around it. But this you can grow into open design proposals. It's not something that's set in stone. And that's really the message I want to leave on, is that there are benefits from this approach, but there's not scripture about it. Find what works for your team and find what works for your organization. And I think you'll find that with very little practice that you're seeing real benefits. And if you give it half a year, you'll find that you're seeing the benefits not only of having good designs coming out the front end, but you have this wonderful archive of things that you've already thought about and the work that's gone into designs over the past half year. So that is it. We've got plenty of time for questions. Like I said, if anybody's doing things similar to this, if this rings a bell or strikes a chord, let me know. I'd love to talk about it. But we have, I think, 30 minutes before lunch, so you can stick around, you can go, whatever. Thank you.
Have you thought about using RFCs as another example?
That's actually a really good point. I hadn't thought about it, but now I will, because that's actually brilliant.
That's what I model my open design.
Okay.
Because that's what I'm used to
Okay.
as an engineer.
Yeah, that's a really good point. It had never occurred to me. I was trying to find some other examples that people would be familiar with, but RFCs are wonderful, so I'm going to write that down. Thank you.
And RFCs have been around since the 70s.
Yeah. Oh, I'm sorry. The question was, have I thought about using RFCs, requests for comment, as an example? And no, I had not, but now I'm going to, because it's a wonderful example of the kinds of things I'm talking about. Yeah. Anything else? Yes?
Have you used these in Agile projects, or is that just more
I've used them definitely in Agile TM projects, as Alan would call them, Scrum projects. I don't professionally have the benefit of being on what I would ever really call a really agile team, one of these gelled, self-organized, flat organizations. But I think it fits, it tracks really well with all the kinds of ideas of agility, right? You tailor the method to method tailoring comes from the agile world, from their literature, so to speak. And this idea of you only write down what you need to write down, minimal documentation, but enough minimal doesn't mean too little, it means just enough to address all of your stakeholder needs. So, I haven't seen it used in what I would call an agile group, but it certainly should be a great fit, I think. Yeah?
you're saying it cuts down the need for testing? Sorry. You're saying it cuts down on the need for testing. Would you see it cutting down on the need for regression testing?
Well, it doesn't cut down the need for testing, but it cuts down the density of defects you discover. Right? You still need to do testing. There's some amount of testing you have to do. This is one of the mysteries of testing, right? That higher quality projects have higher per defect cost, and that's because there's a constant overhead in the amount of testing you need to do. You may, in fact, end up doing more testing with this approach because you'll have a better idea of what needs to be tested. So you have a puzzled look on your face, so maybe
Right.
Okay.
The puzzled look is my default expression.
Oh, okay, good. Then I like you already. Yeah. No, it does. I don't think it necessarily cuts down on the amount of testing you need to do, because I think that's dictated by other engineering elements. You need to test enough to know that your system works. Whether or not you have defects or not, you still have to do the testing. So this may actually increase the volume of testing you do because it tells you exactly what needs to be tested.
Mm-hmm.
Yeah.
Okay.
And sorry, I forgot. Oh, no, you spoke into a microphone, so I didn't have to repeat that. Right. Okay, well, if there are no more questions, grab me later if you want to talk about this. I really would love to have a conversation about it, and thank you again. My name is Austin Bingham, and today I'm going to be talking about, as you can see, open decisions in architectural evolution. This is a talk not about something that I or anybody invented. It's more of a, this material came from observations that I and colleagues have made about different processes, essentially, that have been used in different projects, open source, closed source, private, public, that are superficially different in many ways, but actually have some very powerful commonalities, and I wanted to try to find and understand those commonalities, to kind of like bottle the essence, the important things, and understand why these processes seem to work. I specifically am talking about architectural evolution here because this is the Software Architect Conference. I thought it would be a catchier title. But really, the things I'm talking about here can be used for designs of all scales. It doesn't have to be something architectural, some massive change. But that is kind of what we'll focus on most in this presentation. Does this work? Right, I'm supposed to remind you all, this is to remind me to remind you to download the app and fill in the survey. This is how the conference people get feedback, and it's actually very valuable feedback for me as well, so you can tell me if I did poorly or did well. So please do that. You should all have internet access at this point. So just a little bit about myself. I'm originally from Austin, Texas, this orange dot down here, so any other UT students? All right, hook 'em horns. That's building, and mathematically it all worked out. They could do all the calculations they needed, and they said that yes, this building is not going to fall over. The building was very light, however, because of this new structure, and it meant that the building was going to sway more than normal in the wind. So they put a really clever thing at the top of the building, this 400-ton concrete block, which was controlled by computers. And so if the building sways this way, the computers move the concrete over this way, and the center of mass of the building is compensated for, and it doesn't sway quite as much. So really kind of cool. So you've got one architectural driver down here that forces you to evolve your understanding of skyscrapers, which is this church that you can't move, so you have to build around it, chevron bracing structures, light building, sways in the wind, so you put a concrete block at the top. Everything's fine. They build the building, and it stands. And then Le Mesurier gets an email, and not an email, this is back in the 70s, so I guess a piece of paper, a phone call perhaps, from a grad student. And this grad student says, so I was given your building as a study project, something to do some calculations on so that I can become an engineer and architect as good as you, because he was very famous. And I did these calculations, and it looks like the building might fall over, actually, because when they do calculations for wind resistance on buildings, they do them on the main faces of the building. That, in a standard, normal skyscraper with support at the corners, is the dominant wind factor. And so they did all those calculations and said, yeah, this building is fine. But they didn't calculate enough what they call cornering winds, winds that hit on the corner. And this graduate student wrote to one of the most famous architects on the planet and said, cornering winds are going to knock your building over. It's very susceptible to getting blown over by high winds, which can occur because you're in Manhattan, which is right by the ocean, and there are hurricanes in the North Atlantic. So he, of course, was a bit shocked. He did some calculations, and he determined that, indeed, this building could get knocked over by winds. Now, there are people working in this building now. This is in the middle of Manhattan. There are people all around. If this building falls over, it's catastrophic. Obviously not a good thing. So they basically work really hard to, well, there's actually an interesting twist I should throw in. There was a hurricane out in the ocean at the time. Right, so he calculated initially that once every 55 years, based on meteorological records, winds strong enough to knock this building over would come in off the ocean. So he thought he had some breathing space. But then he did a little more thinking and said, well, wait a second, if there's high winds, even if they're not high enough to knock the building over, things that happen during those kinds of meteorological events are things like power outages. And when the power goes out, that concrete block stops moving around because it's controlled by computers. So now he realizes every 16 years, a wind strong enough to knock the building can come along. So he's really scared now. So they have people inside the building during working hours basically adding rivets to the building to make it more rigid. They don't tell the people in the building about this, which is a little bit weird, but they did tell the police and the fire department, so there was an evacuation plan, but the people working in and around the building had no idea this was going on. So ultimately, they get the building fixed up. It's still standing today, and there's a nice Lego replica, which I assume is in Denmark somewhere, that you can go see. But this, I think, is a really great story with regards to architectural evolution, because it shows that even the smartest people doing things that we've been doing for thousands and thousands of years can make these nearly catastrophic mistakes. And we're doing software, which we've been doing for, let's say, 50 or 60 years, and these are really complex systems, and we are bound to have mistakes and screw things up along the way as well. And so what I want to talk about with architectural evolution is I think I'm pronouncing that correctly, an American with a French last name, so I have trouble saying it. So what is architectural evolution? Changes to architecturally relevant aspects of a system, and particularly to the form of that architecture. There's a distinction in some circles between form and structure in architecture, form being the abstract shape of the architecture and structure being technology applied onto that. People like Jim Copleen like this distinction, and I find it useful. So I am talking mostly about the form of the architecture, changing the shape of the architecture, not so much the choices you've made in implementing it. But I put this picture of this building up because it speaks to the difficulty of architectural evolution. If you've all been through large changes in large systems, you know what I'm talking about. But one thing that stands out with this building, one of the most important things, is if you look on the sides, it's standing on these strange stilts. And it's standing on these strange stilts because there's a church right here. Before this building was built, there was a church, the Lutheran church of some sort, I forget, I've got a note, but I can't see it, that said, fine, you can build a skyscraper here, but you can't move us. We're going to stay in the middle of Manhattan because, of course, that's a great place for a church. So the architect said, well, okay, I think we can work with this. And he designed a system where the load-bearing parts of the building were on the faces of the skyscraper. And this is different from, of course, how almost all other skyscrapers are built. They have load-bearing on the corners. It's a very well-understood architecture that all of the skyscraper builders in New York understood and had dealt with for a long, long time. So this guy, Le Mesurier, had to come up with a way to keep this corner clear and build the building up. So he came up with this chevron bracing structure. I should have a picture of that, but I don't. But that focuses the weight. I'm not a civil engineer, but he focused the weight onto the sides, the faces here, and built the building where I kind of grew up. It's a great city. And why is this not? I'm just going to have to stand here, I think. I like this picture of Austin. Austin the city, not Austin me. This is a statue of a famous local musician, Stevie Ray Vaughan. And in the background is the skyline. It gives you a flavor for what the city of Austin is like. It's very proud of its music. It's very into it. They're the live capital of music of the world. It's a very pretty place, very hot, though. About 6 years ago, I moved to Stavanger, Norway. They're on the west coast of Norway, and this is what it looks like there. This is literally about 30 minutes from my house. This is Lyse Fjord, the best fjord in the country. Don't let anybody tell you otherwise. It's really, really, really beautiful when it's sunshiny, which is 10% of the time. The statues in Stavanger are slightly different, though. These are the three swords. These are 30-foot tall, massive stone swords rammed into the ground, not too far from my house. These commemorate the joining of the three ancient medieval kingdoms of Norway into what we sort of can call modern Norway now. So there's a big sea battle out in that fjord behind the swords, and that's, things are a bit different. They're both wonderful places. If you've never been, you should visit. And of course, 60 North is a company I work for and own and founded up in Norway. So enough about me. First, we have to talk about, if we want to talk about using open design proposals, which we'll get to, for architectural evolution, we should have a common understanding of what we mean by architectural evolution. So, does anybody recognize this building? Maybe. So this is the City Court building in Manhattan. This is actually not the City Court building. This is a Lego rendition of the City Court building. It was the best picture I could find of it. It's certainly the prettiest. This was built back in 1977 by an architect named William Le Mesurier.